Hello! In this video, we are going to prove the following theorem. Let A be a set. Then the number of elements in A is equal to 1 if and only if A is equal to the singleton set of Y for some object Y. Now, before we get into the proof, let's get some context. To start, we're going to say that the natural numbers include 0. And we're going to say that for each natural number n, we define the following set. For each natural number n, we define the set In, which is the set of all positive integers less than or equal to n. Okay, now, what do we mean by number of elements? Well, what we mean here is the following. Given a set A, if there exists a natural number n such that we have a bijection f from In to A, then n is unique. So for example, if we have found that we have a bijection from I6 to A, then we cannot have a bijection from I5 to A, because 6 is the only natural number which can satisfy this condition. Right? And we denote this natural number n as the number of elements in A, symbolically like this. Right, and these type of sets are what we call finite sets. And how do we know that this natural number n is unique? Well, we've proven that in a previous video. And next, what do we mean by singleton set? Well, what we mean here is the following. Given an object y, there exists a set S, such that for all objects t is an element of S if and only if t is equal to y. It turns out S is unique. In other words, S is the only set which satisfies this statement. And we call this set S the singleton set of Y. Now we're just about ready to get into proving this theorem, but before we do that, I would like to show that I1 is equal to the singleton set of 1. How do we do this? Well, all we got to do is show that I1 satisfies the statement that for all objects t is an element of I1 if and only if t is equal to 1. Right? Because the singleton set of 1 uniquely satisfies this statement. If we can show I1 also satisfies the statement, then I1 must be equal to the singleton set of 1. So we're trying to prove a statement about all objects, so give me an arbitrary object. I'll call it t. From here, we want to show this is true if and only if this is true. Since we're trying to prove a statement containing if and only if, we're going to prove if this is true, then this is true, and if this is true, then this is true. Let's start by proving if this is true, then this is true. To do so, suppose this is true. Now remember, I1 is precisely this set where we replace n with 1. So for t to be an element of I1, this means that t is a positive integer and t is less than or equal to 1. But since t is a positive integer, it follows that t is greater than or equal to 1. So we have that t is greater than or equal to 1 and t is less than or equal to 1. These two facts imply that t is equal to 1. So we've proven if this is true, then this is true. Now we're going to prove if this is true, then this is true. To do so, suppose t is equal to 1. Well, we know that 1 is a positive integer, and 1 is less than or equal to 1. So 1 is an element of I1, and since t is equal to 1, t must then be an element of I1. So we have proven if this is true, then this is true. So we've proven both directions of the if and only if. And since t was an arbitrary object, this means for all objects t, this statement is true. So we've proven precisely this statement, which means that I1 is equal to the singleton set of 1. Right, and so we're going to use this fact in proving this theorem. Another fact we're going to use, I forgot to mention this by the way, is the following. Given any two objects A and B, the set consisting of the ordered pair A comma B is a bijection from the singleton set of A to the singleton set of B, right? And we proved this in a previous video as well. So now let's get into proving this theorem. To start, let's give ourselves a set A. And our whole goal is to prove that this is true if and only if this is true. And we're trying to prove a statement containing if and only if, so we're going to prove if this is true, then this is true. And we're going to prove if this is true, then this is true. Let's start by proving if this is true, then this is true. To do so, suppose this is true. So really, we're supposing that the number of elements in A is equal to 1. And based on what we have here, what that means is that we have a bijection in F from I1 to A. Now, we know that I1 is equal to the singleton set of 1. So we can replace the I1 here with the singleton set of 1. Now, since 1 is an element of the singleton set of 1, it follows that F has a functional value at 1. I'm going to call that functional value Y. Right? And since f of 1 is an output value of the function f of 1 must be an element of A. So y is an element of A. Now our claim is that A is equal to the singleton set of y. How do we prove that A is equal to the singleton set of y? Well, remember, given any object y, there exists a set S which satisfies this statement. Right? And we call this set S the singleton set of y. So, to show that A is the singleton set of y, all we got to do is show that A satisfies this statement, where S is equal to A and Y is equal to Y. So, we're trying to prove a statement about all objects, so give me an arbitrary object. I'll call it T. And our goal is to show that T is an element of A if and only if T is equal to Y. Now, we're trying to prove a statement containing if and only if, so we would like to prove if this is true, then this is true, and if this is true, then this is true. Now, we know that if T is equal to Y, then T is an element of A. Because if T is equal to Y, well, since Y is an element of A, T is an element of A. Right? So if this is true, then this is true. Right, so I'm just not going to justify that because it's fine to omit certain details from proofs if it's pretty clear. But now we would like to prove the forward, right? We would like to prove if this is true, then this is true. So let's suppose that T is an element of A. And our goal from here is to show that T is equal to Y. Now, we know that F is a bijection, so F must be surjective. What does it mean for F to be surjective? It means that for every element Q in this set, there exists an element P in this set such that F of P is equal to Q. Right, and that works for every element in this set. Well, since T is an element of this set, it follows that there exists an element I'll call P in this set such that F of P is equal to T. And now, we can show through a chain of equalities that T is equal to Y. To see how that works, well, check this out. We know that T is equal to F of P, that's what we have here. But since P is an element of the singleton set of 1, P must be equal to 1. So we can replace the P here with 1. And we know that F of 1 is equal to Y. So T is equal to Y. So, if this is true, then this is true. So we've proven both directions of the if and only if. And since T was an arbitrary object, we have that for all objects T, this is true. So we've proven this statement, which amounts to proving that A is equal to the singleton set of Y. So we have proven that A is equal to the singleton set of Y for some object Y. So we have proven if this is true, then this is true. That proves the forward. Now we're going to prove the converse. That is, we're going to prove if this is true, then this is true. And to do so, suppose this is true. And our goal is to prove that the number of elements in A is equal to 1. Meaning, we want to find a bijection from I1 to A. Now, we're going to apply this fact, right? If we take A and B to be 1 and y, well, the singleton set of the ordered pair 1, y is a bijection from the singleton set of 1 to the singleton set of y. And we know that I1 is equal to the singleton set of 1, and A is equal to the singleton set of y. Since these two facts are true, we can replace the singleton set of 1 with I1 and the singleton set of y with A. So we have a bijection from I1 to A, which means by what we have here, we have a bijection from I1 to A. Well, 1 uniquely satisfies this condition. So it's another way of saying that the number of elements in A is equal to 1. So we have proven that this is true. Therefore, if this is true, then this is true. So we've proven both directions of the if and only if, which means we've proven this entire statement. And that's exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.